Okay, today is the April 21st, and we're gonna finish chapter 29. And what's chapter 29? Chapter 29 is magnetic force in a current. Okay, so physics note, you go 04 21st 22. Okay, finish chapter 29 today. Exam 2 will be next class on Tuesday. Chapters 26 through 29, 26 and 7, 28, 29. Just like it's indicated here in the syllabus. Okay, so let's just summary what we have done so far. For this chapter, right? Magnetic fields. Then we talked about magnetic force in a charge, on a charge. Then applications of the magnetic field. Real life applications in real devices that are used out there in the industry. The first of them was the velocity selector. Then you combine the velocity selector with external magnetic field and you have the mass spectrometer. Velocity selector plus an external magnetic field. There was another device called the cyclotron that used the magnetic field to accelerate charges. And finally, the Hall effect. What we're going to do now, that's what we covered so far. Today, we will cover the magnetic force in a current carrying wire. Okay, what you have here, magnetic force in a current carrying wire, comes directly from this treatment here that we saw before. Okay, electric current is what electric current is. Electric current is charges in motion. Okay, so inside a wire we have charges moving, and because we know that there might be a magnetic force applied to a moving charge, then we will also have a magnetic force applied to a wire. Okay, so by the same, since we have a magnetic force applied to a moving charge, and a current is nothing but nothing but moving charges, then we must have that if a magnetic field, then if a B field is applied to a current carrying wire, then we must have a magnetic force applied to the wire as well. Okay. The treatment is very easy, we start, how do you find out the magnetic force in a current carrying wire? Well, it's rather easy. Okay. Suppose you have an infinitesimal charge dq in a wire moving with a velocity v. Then the magnetic force applied to the charge dq to the charge dq will be okay, magnetic force dq v cross b. Okay, and then we are going to do something else. We are going to change my v. Let's put also, that's an infinitesimal force as well, because we are talking about a wire, right? Let me see if I can picture that for you. Okay, here you go. Here's a current carrying wire, a piece of a current carrying wire, and we do have an infinitesimal charge somewhere here. Here you go, dq. dq. Here you go. So we must have a magnetic force applied to the infinitesimal charge dq in the wire. This charge is moving. Since the positive charge, I can say that the velocity is to the right. So v cross b, there must be a downward force in this infinitesimal charge. Okay, so that's how you should consider this problem. And here you go. Don't forget that dv can also be written as the derivative of the vector position of the infinitesimal charge dq dr dt. Okay, what's next? Okay, here you go. Next is we commute the dt, take out from the dr and put below the dq. Okay, dt is a scalar, so we can do that. Infinitesimal small scalar, but we can do that. We still can do that. Here you go. And now what we have here? Here we have a current. Okay, here we're gonna have a current dq dt dr cross b, where dr is in the direction of the current. The vector dr the vector dr is in the direction of the current. Okay, and then what we do to solve this problem, we have to integrate this equation in order to find out the net force in the wire. That's what we have to do. And if the current, doesn't change, if the current is uniform, the current can go outside the integral. Here you go. And that's the integrating variable, dr. Notice that this is a vector. Let's do some examples. Simplest of all examples. Examples. Wire, linear wire, straight wire subjected to a uniform magnetic field. Go. Simplest of the all examples. Straight wire of length L, and uniform current subjected to a uniform magnetic field. Solution. Just use this integral. Okay, that's gonna be L cross B. Let's see, dr cross B. Let's go back here to our example. Here you go. We're gonna put a x and y axis here. Here you go. Here you go. We have the x and y axis. Okay, the current's flying along the x hat direction. The magnetic field is along the z direction. So here you go. dr along the x hat okay, magnetic field is in the z direction. Is a uniform magnetic field, so, and also a uniform current, so you can take out both of them outside the integral. IB, we do the cross product between x hat and z hat. I'm doing the step-by-step thing, okay? You don't have to do that. There's a much quicker way of doing that, but but that's the step that we have to do whenever we are using a more complicated approach, a more complicated problem. X cross z is minus y hat. Here we go, minus y hat. Integrate over the wire. The y hat can be taken out of the integral because it's a uniform vector. And finally, we get the length of the wire, L. That's the magnetic force in the wire. And we do have demonstrations of the magnetic force upstairs, okay? We can pass a current through a wire and subject it to a strong magnetic field, and you can see that there is a deflection. We have a demonstration that up there. That's one example. The simplest of all examples, a straight wire. But then you can get something more difficult like that, like a semicircle. Okay? So depending on the direction of the magnetic field here, you're gonna get a given force. Let me take a look here. What the direction of this magnetic field? Ah, okay. The magnetic field is in the vertical direction here. It's in the y direction. Okay, here you go. Okay. That's the notation that we use for the magnetic force in a wire. IDL cross B. Okay, so here you go. Semicircle, radius R, current I. Okay, we should have put the field here in the vertical direction. Good. So here you go. We're gonna have a force over this wire. Yeah, magnetic field is in the vertical in y, positive y direction. Just like we have positive y right in here. Let's copy that. Oops. Here you go. Gonna put magnetic field lines, uniform magnetic field lines. Let's look at this problem carefully. Here we go. You got the idea. I'm not going to. Okay. I'm not gonna do it. Let's see. Right. I think I can. Here you go. Magnetic field in the positive y direction. So here you go. Just do the I cross B. Okay. I cross B. You know, the magnetic field is gonna point towards you. Just like you see in the drawing here. Okay. Here at the bottom, you know, the magnetic field is pointing towards you. But now, since the current is reverting direction, it should point into the board. But it's not just that. It's not just that. Why is that? Because the angle changes. The angle between the current and the magnetic field at this edge is going to be 0 degrees. So the, the magnetic force right here at this spot is going to be 0. And because of that, you know, the magnetic force must increase as the angle gets larger. And then it should decrease back, right? It should decrease back to this point, okay? So just do the right hand rule. Right hand rule like that, right? I cross B into the board. And now we have to use integration. This one you don't have to use integration. This one is easy, right? Is a radius R. Okay. And then we have to worry about this one. Rate for this leg here is going to be IBR. Okay, so just like we got for the other one. IBR. Oh, IBR, no, IB2R. Semicircle. Semicircle of radius R. Okay, magnetic force points along the y-axis. Current flows in the counterclockwise direction. Counterclockwise direction. Find net force. Solution. Wire in the horizontal direction. Okay, so the force in the wire in the horizontal direction is going to be here you go. Here is going to be 2r. Okay, and that's not gonna be y, it's gonna be z. And in this case, it's gonna be a positive z due to the right hand rule. Okay, positive z due to the right hand rule. I cross b. And then what about here? I'm gonna even label F1, that's gonna be labeled F1. Okay. Semicircular wire. Semicircular wire. Now you gotta use this equation here. Let's see, we can do that. Okay, the I is not gonna be in the x hat direction. The I is going to be in a different direction. Okay, the I is going to be in the theta hat direction. Here you go, theta hat direction. The B is in the Y direction, remember? The B is in the Y direction. Let's do that. Continue here. I can be taken out. B can be taken out. And then, you know, theta hat cross Y hat must be in the minus Z direction. Here you go, minus Z direction. Oh, wait a minute, there is one more thing here. Let's see here. Oh yeah, there's one more thing here that you have to take into account. Right, you have to look at the angle as well. Right? As theta varies, there will be an angle between B and the current. For theta equal to 0, the angle is equal to 0. Okay, so there is a cosine term there. Let's see. Yeah, sine term. Okay, so theta hat cross y. So before we put a z, right, we gotta watch out for this problem. It's not z yet. There will be an angle here. Magnitude of theta. Let's write that down. Magnitude of theta. Here you go. magnitude of y, and then that should be sine of theta. Here you go. And you should integrate from 0 to pi. At 0 degrees, the sine of theta is 0, and the magnetic force at that very spot, the magnetic force here at this very spot is going to be 0. Then little by little it starts increasing the magnetic force. Okay, so it's even better to use not dr, but we usually use ds for an arc. You go ds. Oh, don't forget the z hat. Here you go. Oh, it's minus z hat. I'm gonna put that here. Minus z hat. And the ds can be here written as r, the radius of the circle, the theta. Okay, r d theta. And now you can integrate from 0 to pi. Let's see what we get. 0 to pi. R can go outside. Okay, this is z hat can go outside as well because it's a constant vector. You will get a minus cosine for the integral. And the sine cancels out. And then we apply the limits. Nope. From 0 to pi. We don't need that anymore. Go to the next step. Okay, substitute for pi in cosine. You get minus 1, right? Here's the cosine of pi. Here is minus cosine of 0. And then what do we get? We get a force that cancels out with the other force that we saw in the wire, in the straight wire. 2IBRZ minus Z. Okay, so the net force in the semicircular wire is going to be 0. There should be 1 here. Okay, net force 0. That's F2, and that's, F1, 2R. Yeah, so the net force F1 plus F2 is going to be 0. Okay, so that's That's one example that are a little bit more difficult to calculate. And then we have one more example. Here's a current loop in a magnetic field. Okay, so the situation is a little bit like that. Okay, so here you go. Here you go. We have a loop, a current loop. The current is flowing in the clockwise direction. Magnetic field into the board. Okay, and you're going to have some forces in there. Here you go. I1 cross B is going to be downwards. I3 cross B is going to be downwards as well, right? No, let's see. I1 cross B downwards. I3 cross B upwards. Okay. This one, I4 cross B to the right, I2 to the left. Okay, in this case it's gonna be 0. Okay, but if the loop makes an angle, in this case, if you have the loop flat in a surface perpendicular to the magnetic field, the net force is gonna be 0 in the loop. However, if the loop makes an angle with the magnetic field, then something interesting is gonna happen. Okay, the loop is going to oscillate back and forth because even though you have a net force equal to 0, the net torque is not going to be equal to 0. Okay, and as the loop moves back and start moving, then the torque start changing direction as well. The net force is 0, but not the net torque. It's going to oscillate back and forth. You can do that on your own. Okay, you know I do that. Many books and my notes as well deal with that carefully. Where here you go. Here's the force. See, force of 1 in this part of the branch, and this is the force of 3. See, in this case there is a torque. Okay, in this case there is a little torque that's going to make the wire oscillate along this direction. And as it reaches this point here, the net force is 0 and the torque is 0 too, because the forces are collinear with each other. Okay, but because of the inertia of the loop, now the torque is going to invert direction. The loop is going to overshoot the position of equilibrium, and the torque is going to invert direction, and then you're going to have this oscillation back and forth. So that's what you have to know about that, and we are done with chapter 29. Okay, and we can start talking about sources in the magnetic field. So here you go, last example. I'm gonna just last example is a current loop subjected to a magnetic field. Okay, if if two of the I'm talking about a square loop, but it's also applicable to circular loop. Okay, example is a square. Last example is a square current loop subjected to a magnetic field. If two of the arms make an angle with the magnetic force, we will have a net force equal to 0, but a net torque different of 0. Okay, so here you go. This net torque will make the loop rotate Okay, until it is in the vertical, and the magnetic forces vertical magnetic forces are become collinear. Okay, at this point at this point the net torque will be zero, but because the loop started to um, move with an angular speed, because the loop has, you know, because the loop has an angular speed, it will overshoot this position of equilibrium, and the torque will invert direction. In this case, leading to an oscillation, leading to an oscillation of the loop. Okay, that's what you have to know. If you want to see more details, you can, sit down there at home and see how exactly it works. Okay. Now, what we're going to do now is chapter 30. 527. That's good. Okay. So far, we talked just about only about the magnetic field, and we did not state how the magnetic field is created. Okay. So in this chapter, you will learn what is the source, the actual source of the magnetic field. Okay, you already know that there is nothing like that magnetic monopoles, right? Source of electric field, right? What's the source of electric field? It's electric charge. Okay, okay. There is no magnetic charge counterpart. There is no magnetic counterpart to the electric charges. Okay? No magnetic monopole. No magnetic monopole. Nobody has ever discovered that. Nobody has ever discovered that. Okay? So in the previous chapter, we just stated that it was possible to create a magnetic field, a B field, with a magnetic dipole. Okay, a magnetic bar. But what's the basic what's the what really produces a magnetic field? What's those magnetic dipoles are made of to produce a magnetic field? That was something that was discovered some time ago. It was surprising, okay, for the scientists who observed that. Okay, it was discovered. Uh, is that Orsted? It was a. Let me see who the name of the guy is. Let's see. No, this one. It's always nice to go into the history. This one here is who discovered the equation. But there was another guy who found out what was the sources of magnetic field. Okay, let's take a look. Uh, Internet. Who discovered sources of magnetic field? Let's see. Tomorrow's magnetic phenomenon. Not those guys. Magnetic field. Let's see. Source of magnetic field. Electric current. Let's see. So if you want to create a magnetic field, you need an electric current. Okay. Electric current. Okay. Electric current. And who discovered that? Interaction. Let's see. I want to see the history here. I believe it was Orsted who discovered that. Description of magnetic field interactions relation started. It doesn't have all history. Okay. History. Okay. Uh-huh. 1269 mapped out the magnetic fields, okay, of a bar magnet, a spherical magnet, okay. That's the mapping. Gilbert replicated Peregrinus' work, mathematical development, Jean Michel. Uh, Charles Columbus finally verified that the magnetic poles, okay, attracted and repel. But then three discoveries challenged the foundation of magnetic field. Hans Christian Ørsted, yeah, that's him. Demonstrated that an electric current, a current carrying wire surrounded by magnetic fields, circular magnetic fields. So that is the actual source of magnetic fields, a current carrying wire. Every time that you run a current through a wire, you generate a magnetic field around this wire. But because we are talking about dipoles, magnetic dipoles, the magnetic field do not radiate from the source, but they circulate around the source. So that's an important difference between dipoles and monopoles. Okay, if you have a monopole, the field associated with a monopole is going to be radial. But if you have a dipole, the field associated with the dipole is going to circulate around the sources. So, and it was Hans Christian Ørsted, okay, who discovered that. He was a Danish physicist. Close it. Okay, it was discovered. One thing is for you to discover the real source of magnetic fields, okay? Another thing is for you to observe the phenomenon of magnetic field in a bar magnet. Okay, you know that a bar magnet can produce a magnetic field or even small pieces of stone, but what is the actual source of that magnetic field? It's a current. It's an electric current. It's charges in motion, okay? It was discovered that it was discovered by Ørsted that moving charges are sources of magnetic fields. Okay? A current carrying wire produces a magnetic field. A magnetic field around it. We say that the magnetic field circulates around the wire. Okay, that's what we say. Here you go. Why is that? Because it's the very nature of magnetic field. Okay, the very nature of magnetic field is that you do not have a monopole. You do have a dipole, and dipoles, whether it's electric or magnetic, have their field circulating around the dipole. Okay, so here you go. What else do we have to know? Okay, you have to know this equation, the Biot-Savart law of a magnetic field due to a current carrying wire. Okay, so this law is going to be here written a different way. And how is it written? It's written right in here. Here you go. That's how you find this equation by performing experiments. It's a law, right? Magnetic fields can be calculated magnetic fields by a wire, by a current, by magnetic field by a current carrying wire can be calculated by using the Biot-Savart law. So how does it work? Well, it works this way, the infinitesimal magnetic field infinitesimal magnetic field here is equal a constant that we call mu naught, a magnetic constant, mu naught I, the current, okay, ds vector cross, no, cross r hat where is the, oh, here you go, here's the cross, r hat divided by r squared. Here you go. We can put this ds. Oh, there's one more thing, right? Let's put this ds upstairs. It's a very good thing that if you memorize that, because we're talking about a physics law. Here you go. There's a 4 pi downstairs. Remember the inverse of the square of the distance, right? 4 pi. Oops. Biot-Savart law. Let's see how we can, because this ds here is the small section of your wire. Okay, so here you go. How do you calculate that? So let's go step by step here. We're gonna get a generic wire first. Okay, here you go. Generic wire carrying a current. The current is going to be tangent to the wire. Okay, and then what we want to calculate the magnetic field at a position R from, here you go, I'm going to do the following. I'm going to identify, here you go, I'm going to identify the the infinitesimal section of the wire, the magnetic field due to the infinitesimal section of the wire. That's the ds. Okay, remember that ds that you saw there in the equation? That's the infinitesimal section of this wire. And this infinitesimal section of this wire is going to produce a magnetic field somewhere here. Okay? That's going to be given by this ds vector cross r divided by r squared times a constant. The constant is mu naught I divided by 4 pi. I'm assuming that I is uniform. Okay? So that's what we have. Here you go. Let's do that again. Current carrying wire, infinitesimal section of the current carrying wire. This infinitesimal section is going to produce a magnetic field somewhere around here. And we can find out what's the direction of this current by doing the right hand rule. You know, hand pointing along the I, the current I, crossing towards the vector position R. The magnetic field is going to be into the board. But that's the magnetic field due to this infinitesimal wire only. If we integrate the whole thing over the entire length of the wire, you get the net magnetic field that's here at this spot in space. Okay. We don't calculate the magnetic field of this complicated wire distribution, but we can calculate the magnetic field of this loop here. Okay? So if you want to know what's going to be the direction of the magnetic field at the center of the loop, okay, here you go, loop of radius A, right? All you gotta do is to cross I with R. I with R, dB along the Z direction. dB along the Z direction, go. And we're gonna take a look, more careful look here after we come back from the break. Okay, notice that as we, at the very center of the loop, in the plane of the loop, the magnetic field is going to be in the vertical. But then what happens if we go at points higher along the z-axis? The magnetic field is going to make an angle with the z-axis. Okay, and the components of the magnetic field in the xy axis are going to cancel out. So we are going to end up with a magnetic field along the z-axis, parallel to the z-axis. Okay, we're going to do that, but first let's take attendance here now. 1921 today. Mario Acevedo Jimenez. No. Toby. Good. Harun. No. Musa. No. Genesis. No. Jennifer. No. Let me pause my recording here.